All right, so this is a little exercise that kind of sums up the intermolecular forces, and it talks about how you can predict from highest to lowest melting points and boiling points. All right, so remember the highest melting point would be the thing that would be most likely to be a solid at room temperature. The lowest melting point, boiling point, would be the things that would be most likely to be gases at room temperature. All right. So when you're watching this video, feel free to pause it at times and try to look at things and predict what you would think in terms of the order from the highest melting point to the lowest melting point. So first one here, take a look at these three chemicals. All right, which would we expect to have the highest melting point or boiling point? All right, so when you look at these, what's one thing that should stand out? This one right here, that would be an ionic compound. So if you remember from the previous video, that's going to be the class that has the highest melting point and boiling point. All right, so the next are these two right here, and they look to be fairly similar, so how could we tie break between the higher melting point and lower melting point? All right, this one is a slightly larger molecule than this one. This one only has 1, 2, 3, 4 carbons. This would have 1, 2, 3, 4, 5, 6. So you'd expect this would have more London dispersion force opportunities, and that would cause it to have a slightly higher melting point, and then that makes this the last. All right. So the next one, I crossed out one of the cases right here that we had not been talking about. So between these two molecules, all right, at first, they're about the same size. All right, if you calculated the molar mass of this and the molar mass of this, they have about the same molecular weight. So what's going to be the thing that makes one have a higher melting point? All right, notice this has an oxygen-hydrogen bond. All right, that's going to mean it can possibly hydrogen bond, or it will hydrogen bond with its neighbor. All right, that's going to give it a higher, that is a very strong intermolecular force, which causes it to have a higher melting point. This one right here, the only type of intermolecular force it can have is London dispersion forces, and that's a very weak attraction between molecules. All right, so how about between these three molecules? All right, so all of these are very similar in terms of their mass. All right, if you did the molar mass of each of these, you'd find they're about the same. All right, so we can't break that tie based on that consideration. All right, what about hydrogen bonding? Okay, I don't see any oxygen-hydrogen bonds or nitrogen-hydrogen bonds, so they can't do that. So what about dipole interactions? Okay, well, there's no polar bonds in this molecule. All right, what about this? This is polar, the carbon-oxygen is polar. This is also a polar bond. All right, here we've got a polar bond right here. That's the only polar bond in those molecules. All right, so these both have polar bonds, so which one would be more likely higher melting? This has two polar bonds in it. This one only has one, so there's more opportunities for those dipole-dipole interactions to occur in this molecule, so therefore I would call that number one. This one has one opportunity to have a dipole interaction with a neighbor, so I would call that 2. And this one right here doesn't have any chance for a dipole interaction. What is the only type of intermolecular force this would have? The London dispersion forces, which again, all molecules have that have the ability to have those forces, but they are very weak forces, and therefore this would be expected to be lower melting and boiling than these examples. Okay, what about these three examples right here? Okay, so one thing that I hope you're getting used to is every time you see an oxygen-hydrogen bond, all right, that is an opportunity for hydrogen bonding to exist. All right, so if we look through these, we see some of those oxygen-hydrogen bonds, but this molecule right here has got 2 of those types of bonds. All right, that means there's more opportunity for hydrogen bonding here than any of these examples. So this is going to be number 1. And if you're wondering how would it hydrogen bond with a neighbor, I've drawn. Let's pretend one of its neighbors right here. I didn't draw the whole molecule, but this oxygen right here would be the oxygen part of the NOF part, whereas this would be the HNOF part. So a hydrogen bond could exist between there. All right. So between these two, which would be the next highest, well, they look to have the same types. The one difference between these is that there's a couple more carbons in this guy than there are in this guy. All right, so this is a larger molecule. So therefore, London dispersion would be a little bit more prevalent in this one. So I'm going to call, oops, sorry. Actually, this should be number 2. And finally, this one right here should be number 3. All right, so those right there are mixed up. All right, what about between these 3 here? All right, anything that stands out? Okay, this is an ionic compound. It's a metal and a nonmetal, so that's going to be the highest melting. All right, what about between these 2? All right, hopefully you realize there's a nitrogen-hydrogen bond. All right, that means that this molecule can hydrogen bond with its neighbor. That's going to be number 2, and this one right here would be the 3rd. All right, and how about between these 2? That's going to be an ionic compound, and that makes this one, that means since this one is not ionic, it's definitely going to be lower melting than this one right here.